A modern autonomous coding agent can synthesize complex application logic from scratch in just a fraction of a second. Within this text-based environment, the agent operates with near-zero computational latency, processing in milliseconds. Modern software deployments increasingly require native 4K video backgrounds and cinematic visual assets to be integrated directly into the build. While text generation has reached computational escape velocity, high-fidelity visual generation remains bound to the physical limits of heavy cloud processing. Producing just a few seconds of cinematic footage through a model like Google's Veo 3.1 requires minutes of sustained cloud GPU computation. This highlights an architectural mismatch. A millisecond-driven language model is tethered to a multi-minute rendering API. Because language models demand immediate responses, the agent often disconnects and throws an error when rendering takes too long. Without a way to manage this wait time, the agent may hallucinate a fake broken completion URL to bypass the delay. Without a dedicated buffer to bridge this time gap, autonomous agents cannot reliably handle high-end media, completely stalling fully automated production pipelines. The Higgsfield Model Context Protocol, or MCP, functions as a decentralized bridge designed to manage this latency mismatch. When triggered, the agent submits a data payload with generation parameters. The server immediately returns a lightweight job receipt and a processing status, keeping the agent connected. Using wait for job, the agent pauses its main thread, periodically pinging the server for completion. Once the cloud cluster finishes the render, the next ping retrieves the final asset URL, pulling it into the active conversation. This asynchronous architecture effectively allows our instantaneous cognitive agents to work in perfect parallel with heavy, high-latency cloud rendering clusters. Deploying this level of autonomous routing introduces a specific engineering challenge: context window bloat. To route these requests accurately, the agent must hold the detailed schemas for over 30 distinct media models in its active memory. Loading these model definitions consumes approximately 12,000 tokens before the user types their first prompt. If left unmanaged, this bloat forces the agent to reprocess the entire tool library with every message, leading to rapid API exhaustion. Making this system sustainable requires active context pruning to ensure that the automation remains cost-effective at high volumes. In an optimized workflow, a developer can prompt an agent to build a complete web application from within their IDE. The agent writes the front-end logic while simultaneously dispatching a video generation task to the MCP in the background. Through the Sole ID capability, the agent retains a specific identifier to guarantee that character faces remain consistent across every asset in the campaign. Once the MCP returns the finished asset URL, the agent automatically embeds it into the source code for the live deployment. This unified loop removes the operational friction of round-tripping assets between separate design and engineering teams. This terminal-driven approach bypasses the traditional requirement of jumping between disparate graphical user interfaces to manually place and render files. In high-volume content cycles, code-driven orchestration now handles the assembly and placement of assets that previously required manual work on a video timeline. The role of the technical creator is shifting away from frame-by-frame manipulation and toward the design of high-level systems architecture. This shift in production highlights the rise of context engineering, where operators focus on building the autonomous infrastructure required for creative scale.